We're going to continue on. We're talking acid and bases here. The last chapter before we get into organic. So a couple of reminders. Acid here is any substance that has the ability basically to produce H plus. And remember that when we talk about sort of acid-base chemistry, H plus and H3O plus, which is the hydronium ion, they're pretty much the same thing. So they are sometimes used interchangeable, again, both in sort of formulas, also in reactions and equations as well. So, for the most part, anywhere you see an H plus or you see an H3O plus, you can interchange them. They really do represent sort of the acidic part of the solution. And what makes something an acid, again, is that ability to produce those guys freely floating. So, again, just the ability to produce free floating H plus in the solution will make it an acid. A base, on the other hand, is something that can produce hydroxide ions in solution. And it's sort of, again, the same idea here. It is something that has that ability to produce OH minus ions in the solution. Again, these things are not attached to anything, so they're just kind of free floating. And whatever substance that can sort of produce that is considered a base. Now, not all bases will have, for example, hydroxide in it. And a lot of times when we talk about acid-base chemistry, we use a little bit more of a general sort of definition of acid and base, and that's the Bronsted-Lowry definition. In the Bronsted-Lowry definition, an acid is a proton donor. And again, an H plus, which is the hydrogen ion, is oftentimes referred to as a proton in acid-base chemistry. Again, because a hydrogen has one proton, one electron, and no neutrons. So for it to become positively charged, it had to lose its electron, which leaves it just a proton. The base is something that can basically do the opposite. It is a proton acceptor. And sort of the consequence of the Bronsted-Lowry definition of an acid and base is it actually will create partners on the other side of the equation. So if you take HCl and some water in this case, here hydrochloric acid is going to donate the H plus over. It will make the hydronium ion and Cl minus in this case, right? And this would be our acid. Our water in this case would be our base. And again, it will create partners on the other side where the Cl minus is known as the conjugate base to that acid, while the H3O plus would be the conjugate acid to that base. Remember that the only difference that you could have in order for those guys to be pairs is just that one H plus difference. So if there's anything more than one H plus, they're not considered pairs. And the idea there is somebody will transfer one H plus, somebody will accept one H plus, and it will create those sort of things. We can even see it, for example, here, if you look at ammonia, which is an example actually of a weak base plus water. In this case, it's actually going to be the NH3 accepting the H plus, and that will create NH4 plus and OH minus. In this case, the NH3 will be our base. Water in this case will be our acid. Partner on the other side, whoop, too far. There is the conjugate acid. And our acid here, partner on the other side, would be the hydroxide, which would be the conjugate base. Again, just one H plus difference between them. Here, the acid will end up with one less H plus when it goes to the other side because it gave it away. And the base will have one more H plus as it accepts that proton from the acid. This also brought up something that we talked about, which is something like water, for example, can act as an acid or base. And there are certain things that could really go both ways, and those guys are what are known as being amphoteric substances. Amphoteric substances are, again, substances that can act as an acid or a base depending on the situation. Again, water is an example of that. It can basically do both things. The other thing that we sort of talked about again at the beginning was just general reactions of acid and bases. And remember that when you do have a reaction of an acid and a base, especially a strong acid and a strong base, you will always basically get two things that are formed. That will give you your salt and water. So that's always what you're going to make it from. The water always comes from the H plus and the OH minus from the base. That again is how we get to the water. The salt is just an ionic compound. So basically the other ions will come together and make an ionic compound. So if we did something like hydrochloric acid plus some sodium hydroxide, that again is a strong acid, strong base. It is also a double displacement reaction, positive, negative guy, positive, negative guy. Again, the H and the OH are going to come together, and the sodium and the chloride will come together, and they will switch partners and make sodium chloride, which is our salt. And obviously, again, the H from the acid, the OH from the base will make that water here that we will produce in this case. Any questions on any of that stuff we talked about, I think, last time there? Okay, so I think we did an example at the end there on Brunstad-Lowry, and I think we have another example to look at. So why don't you do that? Okay, so let's take a look. And again, hopefully at this point, you know that the only difference is one H plus. The key is to know should you put it on or take it off is really the important thing to try to figure out. So this is where understanding the relationship of Bronsted-Lowry really could help you determine that. We know that we have an acid on one side there and a base, and then we have some conjugate partners on the other side, acid and conjugate base. So we know that if it's the acid on this side, it is related to the base on that side. And if it's the base on the left side, it is related basically to the conjugate acid. So in this particular case, we are looking for the conjugate base. So that is what we want to write, which means that is where we want to end up, which means if you think about it backwards, we are starting with an acid, and all these guys would be an acid in this particular case. And we just has to go at this point by the definition of Bronsted acid, which is it should donate the H plus. So again, you can kind of think about it backwards and figure out what each of these things are. They will not always, like in problems, tell you, hey, these are acids or these are bases. They'll just ask you to write something like the conjugate acid or conjugate base. So if you sort of think about it backwards, we know that these are acids, which means we should lose an H plus here on all these. So if we take away an H from this first guy, we are left with one H and an S. Remember that it is not just the H, but it is the H plus, which affects the charge. So when we lose a positive charge, we become one more negative. So it should be HS minus in this case, again, since we started at neutral. So when we lose that positive charge, one more negative would take us from 0 basically to -1 in that case. Question on that there. Looking at the next one here, we're again going to lose an H plus. So we're going to take off the H. That leaves us an S. This already started at -1, which means we become one more negative, which means we need to actually end up at -2 in this case. Any questions on that there? NH3, again, we're going to lose an H. That leaves us only two H's. Once again, it was neutral here, so we do become one more negative, which will give us NH2 minus. And lastly here, H2SO3, sulfurous acid, We will lose one H, still have everybody else. And again, we were neutral, so we will become one more minus. Any questions on any of that there? Now, let's say we had something like HCO3 minus. Why don't you write the conjugate acid for that one? And why don't you also write the conjugate base? So in each cases, you're going to start with this guy. What would be the conjugate acid? And then what would be the conjugate base for that guy? So take a moment there and see what you end up with. Okay, so once again here, we're going to start with our HCO3 minus, which is our bicarbonate. We'll start with the conjugate acid. So once again, we do want to end up over here and write the conjugate acid. So if you again think about it backwards, that means the partner on the other side where it originated, this guy is actually going to be a base in this case. So a base, a Bronsted base, is something that will actually accept the H plus. So in this case, it's going to accept the H plus, right? So it's going to gain an H plus, and that would mean that our conjugate acid here is going to be H2CO3. Again, putting the H on, +1 -1 gives you 0. Now, if we look at our conjugate base, just like we did in the problem, that's where we want to end up. If we go backwards, that means we're staring now at an acid, which means it's going to lose an H plus, right? It's plus an H plus and minus an H plus. And that will leave CO3 to minus when we take the H off. And we again become one more negative because of the plus, because we started at -1 to begin with. This is another example of a substance that can be amphoteric. It could act as an acid or a base. Usually if you have a substance like this where there's a hydrogen and like a negative charge, it usually has the ability a lot of times to act either as an acid or base in the situation. If you don't have the hydrogen, then it can't give it away, so it can only act basically as a base. Any question on Bronsted-Lowry definitions there? All right, so obviously you need to be able to identify those, write the proper things. And again, sort of thinking about it backwards, like we did there at the top, is a good way to sort of identify what you're looking at. And then you just need to go by the Bronsted-Lowry definition. Any questions on that there? Yeah. So let's talk a little bit about acid strength. As I mentioned before, there are obviously strong acids. There's also weak acids. And in the forward direction here of our acid, here again, our water would be acting as the base in this case. This is our acid. This would be our base. This again is just a generic formula for any type of monoprotic acid, which has one hydrogen basically to give, like HCl, HBr, whatever it may be there, HNO3. Now, in certain cases, depending on the acid, these guys that are formed over here could then actually head back the other way, and this would be our weak acid in this case. It's a weak acid. It's like a weak electrolyte there. We have those arrows heading in both directions, like we talked about with weak electrolytes. Again, this would be an example, something like hydrochloric acid, strong acid. Down here, something like hydrofluoric acid, which is a weak acid in this case. Now, if the forward direction predominates, we do have a strong acid, which means it will 100% break apart. So remember, there's sort of that list of 6 or so strong acids. Again, that is hydrochloric acid, that is nitric acid, that is sulfuric acid, that is perchloric acid, That is hydrobromic acid and hydriodic acid. These are pretty much 6 really strong acids. The nice thing about knowing those 6 acids is you could very easily know if you have a strong acid or not. If it's not one of these 6, probably dealing with a weak acid. So this is an easy way to sort of determine if it's weak or not. What that means, again, completely ionized or completely dissociated, what that means is that strong acid is going to be a strong electrolyte and will 100% break apart into ions. So in a solution of hydrochloric acid, you have basically none of those guys still together. They have all completely broken apart into ions, basically. And that is why it's considered a strong acid, because all it has to do is go for a swim. It's going to produce a lot of free H plus in the solution, which is your definition of an acid, is that ability to produce that H plus or H3O plus in solution. And again, that's going to completely produce a lot of it because it's going to completely fall apart. That's different again than in a weak acid like our hydrofluoric acid. Our hydrofluoric acid, when it does break apart, will do the reversible reaction. And again, in this case, you will actually have mainly this guy actually still together. So it'll actually mainly stay together because it's a weak electrolyte. And what that means, if you look at a solution of hydrofluoric acid, you will have a lot more of the whole units together, which frankly doesn't do great for making it an acid because the hydrogen stuck to the fluorine basically, so it doesn't come apart. But it will produce a little bit of ions in solution. So since it's still able to break apart just a little bit, it's able to produce a little bit of H plus and still be considered an acid. Nowhere near the amount of H plus that something like hydrochloric acid would produce, because all it has to do is go in there, it's just going to completely fall apart. Our hydrofluoric acid or weak acids is to kind of stay together, but will produce a little bit of those ions. So you'll get a little of these guides, which is why it's still an acid, but this is mainly what you would have in a solution. Any questions on that there? So hydrofluoric acid, acetic acid is another weak acid. HNO2, nitrous acid, is a weak acid. Carbonic acid, there's a lot of them, but it's much easier to know the strong acids and just know that if it's not one of those, then it's probably going to be weak. The relationship between sort of the acid and base and its conjugate partner is, if you have a really strong acid or strong base, its conjugate partner on the other side of the arrow will be what is considered relatively weak. So it's sort of an opposite relationship. So if you have something like hydrochloric acid, that's my acid, this is my conjugate base. This is relatively strong, and this guy would be relatively weak, the partner there. It's relatively weak, and really what that means is it's considered, frankly, a neutral salt. It will just kind of hang there and float around, not really do much, not really affect the pH. It's relatively weak. Now, if you have a weak acid or weak base and its conjugate partner will be relatively strong. So, for example, if you take hydrofluoric acid, like we were just talking about, and you got your water there, going to produce your H3O plus, if you include the water, and F minus. This would be my weak acid. This would be my conjugate base. And because this is weak, its partner over there is going to be relatively strong. And what that really means, which is really outside of sort of our class, but what actually happens and why it's sort of considered relatively strong in a sense, it is not as strong as a strong base or anything like that, but it's strong in the sense that it actually would have the ability, for example, that F minus, to actually go find water and do a little reaction, and actually take an H plus from water, and it will form HF. And actually, this is the important part of it, it will actually form some more hydroxide. So because you have that conjugate base, in this case, in the solution, it actually will not just float around, not do anything. It actually will start reacting with water and go through a reaction, which is what is referred to as a hydrolysis reaction. And again, we're not going to go too far into this, but basically what it will be able to do is produce more hydroxide. And that would have an effect on the pH of the solution because now you just created more hydroxide. You're going to actually make the solution more basic because of that, because of the presence of that guy. So there are certain salts that are conjugate acids or bases that actually are relatively strong in the sense that they can continue to react with water because water's in the solution to begin with and can either form more H plus or form more OH minus and actually have an effect on the pH. But any sort of conjugate partner that came from a strong acid or strong base won't do that. They'll just float around. They won't react with water. And that's why they're considered neutral and stuff like that. Any questions on that there? So we had our list of our strong acids. Something like sulfuric acid is actually a diprotic acid. And diprotic means that it could give away two hydrogens. Monoprotic, which is HA, for example, has only one hydrogen to give. Diprotic has two hydrogens to give. And there's also triprotic acids. H3A has three hydrogens to give. Examples of each of those, monoprotic would be like hydrochloric acid is an example of that. Our diprotic acid is also sulfuric acid, like we're going to look at there on the bottom. And our triprotic acid would be something like phosphoric acid is a triprotic acid. Now, if you have something that actually can give away more than one hydrogen, like sulfuric acid, like phosphoric acid, they actually give those hydrogens away one at a time. They all don't just fall off at once. They actually come off in what is referred to as a stepwise fashion. What would happen in the case of sulfuric acid is that guy would release one hydrogen only and make HSO4 minus. Then what would happen is that HSO4 minus will then release a second hydrogen and make sulfate. So they actually come off one at a time. They don't both, even though we sometimes see the overall reaction where it appears that they both just sort of fall off together. They do come off in a stepwise fashion. If you had to guess, which one would be easier to take off, the first one or the second one? It is going to be the first one is much easier because after you take off the first one, you now have something with a negative charge and you're trying to remove something that's positive, right? Opposites attraction to each other. So it's going to hold it tighter. It's going to be harder to remove the second one. In the case of phosphoric acid, H3PO4, it's like super hard to remove that third one. Very little of it comes off. Actually, most of the hydrogens when you have a diprotic or triprotic acid, most of the hydrogen that comes off is actually just the first one that comes off is the majority of it that comes off because it gets much, much harder every time you try to remove an extra hydrogen. That is also why when we talk about Bronsted-Lowry definition of conjugate acid base pairs, this guy and this guy are pairs. This guy and this guy are pairs because the only difference between them is one H plus. That is also why if you go from this guy directly to that guy, they are not pairs because that is two hydrogens that came off. So again, only one hydrogen at a time for them to be pairs. That's why H2SO4 and SO4 2- are not conjugate acid base pairs because it's two steps down the road there rather than one because they do come off one at a time. Any questions on that there? Yeah. All right. So we talked about water acting as an acid or base. Water itself can do that, obviously. And when water reacts with itself, one water will act as the acid, the other will act as the base. It's kind of what's happening all the time when you got water going on. One will be the acid, one will be the base. In this case, then we're going to send an H plus over. That will make H3O plus and OH minus in solution. And this is what is sometimes referred to as the autoionization of water. And there's a really important relationship that happens when water reacts with itself. And it is this relationship, which is known as Kw. And Kw is equal to the concentration of H plus times the concentration of OH minus And for the most part, it equals 1 times 10 to the minus 14. When you see these little brackets, that means concentration. And usually we're talking about molarity, which is our moles per liter, is basically what we're talking about here. So again, as I mentioned before, this is where you can interchange H plus or H3O plus. Again, Kw could also be written H3O plus times OH minus equals 1 times 10 to the minus 14. Again, the H plus and H3O plus are basically the same thing. The H plus is the acid part of the solution. The OH minus is really the base part of the solution. This is something that you could use to calculate if you know what the H plus concentration is or H3O plus concentration is. You could calculate the OH minus concentration, and you could actually figure out is the solution acidic, basic, or neutral based on how much H plus or H3O plus you have in there and how much OH minus you have in there. The relationship between H3O plus and OH minus is an opposite relationship. As one goes up, the other goes down, and vice versa. As one goes down, the other goes up. So they go opposites of each other. So as one goes up, one goes down. When you have that H3O plus or OH minus part of the solution. So that is really a formula that you should think about knowing, because this is how we use it. Since Kw is a constant, so this is the Kw value there, 1 times 10 to the minus 14. You definitely, as a reminder, want to make sure that you are using your exponent button when you punch these things in your calculator. Otherwise, you're going to be in real trouble in this chapter. Yeah, so make sure scientific notation, exponent button. The good news on this calculation is it's the same regardless of which one you have. You basically take 1 times 10 to the minus 14 and you divide it by whatever number they gave you, basically the H plus or the OH minus. So if you compare and the H plus concentration is larger than the OH minus, so basically the acid part of the solution is bigger than the base part of the solution, it's going to be an acidic solution. If you look at it in the OH minus concentration that you calculated is larger than the H plus concentration, that means the basic part of the solution is larger than the acidic. It's going to be a basic. And if they do equal each other, they actually both will have a concentration of 1 times 10 to the minus 7. That's going to be a neutral solution. Any questions on that there? All right, so let's grab our calculators and see, shall we? Here, let's try some. And again, make sure you use your exponent button. All right, so each of these are separate problems. So do each of these. Calculate either the H plus concentration or the OH minus concentration, depending on which one's given to you. Calculate the opposite and then decide, is it acidic, basic, or neutral? So the first one, we're going to look for the OH minus. OH minus for the second one, H plus or H3O or H3O plus for the third, H plus or H3O plus, whichever way you like to word it there. All right, so give it a go, see what you come up with. Now it does say something about temperature, and that's really just telling you that it's under normal conditions. You don't have to do anything with the temperature. I will say probably not in our class, but the Kw value does change with temperature, but usually it's a constant value, that 1 times 10 to the minus 14. You can consider it. If it's not, they'll give you a different number for a different temperature, but that's why temperature is sometimes included in these problems, just to let you know, hey, you should use that 1 times 10 to the minus 14 number. All right, so take a few moments there, calculate it up, and as each look to see how you're doing. So again, in this situation, if you need to figure out the H plus concentration or OH minus concentration, it is that Kw relationship that the H plus times the OH minus concentration equals 1 times 10 to the minus 14. So you could think about that number as a number you always have sort of available to you. And again, this is another place where if you wanted to do H3O plus, same thing. So let's take a look at the first one here. This case, they gave us the H plus, which means we're going to rearrange that. And it really doesn't matter which one you're solving for. It will always rearrange the same way. OH minus equals KW times the H plus, or divided by the H plus concentration. That's going to be our 1 times 10 to the minus 14, which is what KW equals. And we're going to use the concentration that was given to us, 2.6 times 10 to the minus 8. Again, we want to make sure that we do use our exponent button. So a throwback to how to punch it in correctly, just to remember, 1, your exponent button, your negative button, and 14, then a little divide button, 2.6, exponent button, negative button, and 8, and an equals. Yes. So again, that would be the right way to punch it in. Make sure you're definitely using your exponent button in this chapter. And that's going to get you, looks like 3.8 times 10 to the minus 7. You do need units, and it's usually molarity because we are looking for a concentration, and those were the units on the original concentration in this case. First off, any question on the calculation there? Now we want to know, is the solution acidic, basic, or neutral? So to do that, we're going to compare the H plus concentration, which is really the acid part, to the OH minus concentration. And in this particular case, which one is larger? It is the OH minus concentration is larger. 10 to the minus 7 is a larger number than 10 to the minus 8. Remember, the negative there on the exponent's important because 2.6 times 10 to the minus 8 means you're going to go this way 8 places and put zeros, versus 3.8 times 10 to the minus 7, where you're just going to go 7 places that way, and that will actually make it a larger number. So when you're comparing negative exponents, the smaller negative exponent is actually the larger number. So just keep that in mind. Sometimes people get that backwards. The negative is kind of important there. So this guy would be basic in this case. By the way, when you're asked that question, is it acidic, basic, or neutral? There's just one answer. Yes. Cannot be acidic and basic at the same time, although I've seen it on a lot of tests. And I've never seen all three. Nobody's ever given all three, like acidic, basic, neutral at once, but I have seen both. Thank you very much. Any questions on that calculation there? All right, let's take a look at the other ones here. In this case, I feel like I missed one. Did I miss one? I did. I missed the first one off. So here, when we do the first one, since I apparently missed it, we'll go back here. So for the first one here is again going to be the same calculation. It's going to be the OH minus concentration is equal to KW times the H plus. That will give us the OH minus concentration is equal to 1 times 10 to the minus 14 divided by 3.4 times 10 to the minus 4. And again, punching that in properly there. 1 times 10 to the minus 4 divided by 3.4 to the minus 4. That's going to give us, for the first one there, 2.9 times 10 to the minus 11. That also would be molarity in this case. Now, in this case, our H plus concentration is 3.4 times 10 to the minus 4. Our OH minus concentration is right there. It is the H plus concentration that is larger in this case than the OH minus concentration. And that means that in this case of the first one, it would be acidic in this case. Any questions on that one there? Again, 2.9 times 10 to the minus 11 means you got to go 11 places to the left there, put a bunch of zeros in front of it. It's going to make it a really small number versus the other guy. Any questions on those two? All right, let's take a look then at the third one here. We have an OH minus concentration given to us. And it really doesn't matter which one's given to you. It's going to be the same calculation. The H plus concentration will equal our KW divided by our OH minus concentration. And that's going to give me 1 times 10 to the minus 14 divided by 6.2 times 10 to the minus 9. That's going to get us here, again, making sure we use our exponent button. Looks like 1.6 times 10 to the minus 6 molar. In this case, when we compare our H plus concentration to our OH minus concentration, really you could usually only just need to kind of compare the exponents there. And again, here, the H plus is actually a larger number than the OH minus. So it would be acidic in this case. Questions on that one there? Last one here is we got an OH minus of 8.1 times 10 to the minus 3. That would mean that our H plus concentration would be 1 times 10 to the minus 14 divided by the OH minus. Going to give us 1 times 10 to the minus 14 divided by 8.1 times 10 to the minus 3. And that's going to get us here. Looks like 1.2 times 10 to the minus 12 molar. That means in this case, our H plus concentration is actually less than our OH minus concentration, comparing to the minus 3 to the minus 12 in this case. That means that this solution would be basic. Any questions on any of those calculations? Again, most people struggle with putting it in incorrectly, not using, again, the exponent button is really the important thing there. Any questions on those there? All right, let's try a few more here. Make sure. Got. All right, let's not do what it says. Let's just calculate what is the OH minus concentration here. And is it acidic, basic, or neutral? That's what you come up with. Okay, so let's take a look. Again, we will solve for the OH minus by taking our KW divided by the H plus, or H3O plus, gives us 1 times 10 to the minus 14 divided by 2.8 times 10 to the minus 5. Once again, 1 exponent button, negative button, and 14 divided by 2.8 exponent button, negative button, and 5 in that case, and a little equals. So if you do all that good stuff there, you should end up with 2.6 times, no, that's bad. Try that again. How about like 3.6 times 10 to the minus 10 molar in this case? Again, remember when you do these calculations, you may not always get it in scientific notation, may have a decimal form in your calculator that you might need to turn into scientific notation. Here again, we do want to compare the H plus concentration with the acid part to the OH minus, and looking at really just the exponents here, that's to the minus 5, that's to the minus 10. Minus 5 would be a larger number, so in this case, it's going to be acidic. Any questions on that? Questions on how to calculate using KW here. All right, then let's take a look at, let's get that example. Let's talk about another way we can look at acidity, and that is the pH scale. Bless you. And the pH scale is really a measure of acidity. The pH scale runs from, we'll go down here, 0 to 7 to 14 is the pH scale. Less than 7 is acidic. Above 7 is basic. And really at 7, where the concentrations equal each other, that's neutral. And as you go from 7 towards 0, you become more acidic. And if you go from 7 towards 14, you become more basic. So to calculate the pH, it actually tells you in the name what you need. pH means you need the H plus concentration or the H3O plus. So it basically tells you in the name that's going to be negative log of the H plus concentration. This once again is another formula that you could swap out the H plus for H3O plus. They mean basically the exact same thing. So whatever way is listed, H plus, H3O plus, same thing, pop it into that equation. That will give you your pH. So let's talk about calculators and how to punch it in correctly. Depending on if you have a display calculator or a non-display calculator as to how you should punch it in. If you're not sure what type of calculator you have, just punch the log button, hit the log button. And if it says log, congratulations, you have a display calculator. If it says error, congratulations, you have a non-display calculator. So if you hit log and you see log, you have a display. And if you hit log, it says error, you have a non-display. If you have a display calculator, you're going to punch this formula in and all the other ones that we'll see in this chapter just the way they're written. So if you have a display, you're going to roll with the negative button, the log button, and then you're going to put your number in with your exponent button, basically. If you have a non-display calculator, this one and all the other ones we're going to see, you got to roll backwards, which means you need to start with the actual number. You then need to hit the log button, and then you need to hit the negative button. So depending on which way you have in terms of your calculator, display, you go forward. Non-display, pretty much going to roll backwards. So it's the way you need to punch it into your calculator. By the way, this is not negative. That's just from PowerPoint, obviously. So the pH is there. So let's talk a little bit about pH and significant figures. The rule for pH is the number of decimal places you should have in your pH value, or a value like that, should equal the number of significant figures in the concentration. So however many significant figures there are in the concentration you're using to calculate your pH or a similar value is how many decimal places you should have. So we'll talk about what that really means in 1 second. So why don't you calculate the pH if you have, what is the pH if you have this concentration for H plus? So why don't you calculate it? First off, make sure you know how to punch it in your calculator correctly. And then we'll talk about what you should give the answer to when you do it. So again, display calculator, go exactly the way the formula is written. Non-display, go backwards. So if you punched it into your calculator, you should be staring at the number 5, I hope. Yes, so you should be staring at the number 5 on your calculator. Again, we should be using our pH equation, negative log of the H plus concentration. Again, it tells you need the H plus. That's exactly what we have. So that means that the pH in this case would be negative log of 1 times 10 to the minus 5. Again, if you have a display calculator, you would punch this in the negative button, not the subtract button, the negative button, the log button. You would hit 1, your exponent button, your negative button, and 5, and then hit equals. If you have a non-display calculator, you're going to go roll backwards. You're going to do the number first, 1, exponent button, negative button, and 5. You then will hit the log button, and then you will hit the negative button, and you should have 5 staring at you no matter which way you go. That would probably take care of 99.9% of people's calculators, I think. And you do have 5. And now how should we record it? 5, 5.0, 5.00. What should be the proper way to record this? So the rule says that the number of significant figures in our concentration, that is this number, right? How many significant figures does it have? It has 2 significant figures. Is how many decimal places, not significant figures, there is in the pH. So you're going from significant figures to decimal places. So the proper way to record it is actually 5.00. By the way, it works going backwards. If you go from pH back to concentration, which we'll talk about, if you have 2 decimal places, your concentration should have 2 significant figures. So it works going both ways when you do it. First off, any question on that there? Yeah. How do I know what now? Are you talking about this negative? Yeah, that is always negative there. That's always the formula. So you need that. If you don't use it, you'll end up with a negative pH. So it's always negative, that one, and it's always in that formula. So that's just the formula how you calculate it. Other questions? By the way, is this acidic, basic, or neutral, this one? It is acidic, yeah, it's less than 7. So when you look at the pH is less than 7, it's acidic. Any questions on that there? All right, let's try a few more here. Now you got your calculator out, yeah? All right, for each of these solutions, what's the pH value? And is it acidic, basic, or neutral? So take a moment, grab your calculator, make sure you know how to use it. So 2 answers here, one for solution 1 and one for solution B2. Is what's the pH and is it acidic, basic, or neutral? Both of them. All right, so let's take a look here. We're gonna look for the pH here. So for number 1, we're gonna go pH is equal to negative log of the H plus concentration. We have the H plus concentration, so we can put it right in. And again, we want to make sure, obviously, we punch it in correctly, depending on whichever way your calculator works. And mine works differently. It's a little bit. And that's going to give us a pH here of 4.68 here. Again, we have 2 significant figures, means that we end up with not 2 sig figs, but 2 decimal places as we go to the pH. Acidic, basic, neutral, this one? It is acidic, again, less than 7. Question on that one there. Now we go number 2. We want to calculate the pH is equal to negative log of the H plus. Hopefully you notice that is not the H plus concentration. That's the OH minus concentration. So we could use our KW like we did earlier to get the H plus, which would be KW divided by OH minus. That would equal 1 times 10 to the minus 14 divided by 5.9 times 10 to the minus 8. That will get us here 1.7 times 10 to the minus 7 molar. That is our H plus. So we can now go into our pH minus the log of 1.7 times 10 to the minus 7. And if we do that good stuff there, not hit too many buttons like I just did, gives us a pH of 6.77 actually is our pH. That is slightly acidic, yeah. We're gonna go with 7 on the nose is neutral, yeah. Some people go a little higher, a little lower, but just so there's no misunderstanding, 7 on the nose would be neutral, because that's when the concentration is equal to. Now, if you didn't read that and you just decided, hey, I'm gonna throw it into the equation here, the original number, and you did negative log of 5.9 times 10 to the minus 8, and you did that. And you get 7.23. You did not obviously calculate the pH, because we just calculated the pH and it's not that number, because this was not the H plus, this was the OH minus. But what you did calculate was 2 slides down the road, what's known as the POH. That is the POH. And sometimes that's very useful because there's a really handy relationship that if you take the pH plus the POH equals 14, which means my pH would then be 14 minus my POH, which in this example would be 14 minus 7.23. Get you a pH of 6.77. So again, you can calculate the POH if you have the OH minus concentration. It's the exact same calculation as the pH, basically, except that you use the POH or use the OH minus concentration. Again, it tells you in the name POH, you need OH minus. pH, you need H plus. Basically, it tells you what you need to calculate that. So sometimes that's a quicker way to get to the pH rather than using KW. If you still want to use KW, you can, as you can see here, and you'll get the same answers. So there are a couple of different versions or ways that you could solve for these problems depending on what's given to you. Any questions on that there? Question? Yeah. Yeah. If you have the OH minus and you want the pH, you have two options. You can either do the KW to convert it to H plus and then go into the pH equation. Or if you want, you could do the POH equation and then take 14 minus that number and it'll get you the pH. So there's two ways that you could get it. Basically, yeah. So whichever way you prefer, they both should give you basically the same answer at that point. Any questions on that? Yeah. Are we talking about like the pH and all that? Is that what we're talking about? Yeah. Yeah. So the rule is not significant figures to significant figures. The rule is basically significant figures, which is 2, to decimal places, not significant figures. So to 2 decimal places. So a sig figs to decimal places in that case. Yeah. Yeah, so if you're having trouble doing that, just come see me after class and we'll figure out on yours. But those are usually the two most common ways. Again, if you have that other one with the dial, you make sure you still are putting your number in parentheses, when you punch it in. Other questions on that? All right, so as I mentioned before, and as we sort of saw a second ago, we sort of jumped a couple of slides. That's the ones we just did, I believe. So when we look at the pH scale, it is based on the power of 10. And for every 1 pH that you change, the power of 10 changes. So if you have an H plus concentration of 1 times 10 to the minus 3, that is a pH of 3. You have 1 times 10 to the minus 4 is a pH of 4. 1 times 10 to the minus 5 is a pH of 5. By the way, if you're getting at the pH of anything, that's 1 times 10 to the minus whatever, that is the pH. As long as it's 1 times 10 to the minus 7, there would be a pH of 7 and so forth if you have that. The pH value goes down as the concentration of H plus goes up and the OH minus concentration goes down. The pH will go up as the concentration of H plus goes down and the concentration of OH minus goes up. So remember, those guys go opposite of each other. So as one goes up, the other goes down. So really low pH means you have a lot of H plus in the solution. A higher pH means you have actually more OH minus than you do, especially if it's basic, you have more OH minus than you do H plus in that case. Now, how can we measure pH? Here's two very common ways that you can measure pH. You can use a pH meter, which is this electrode. You basically just stick it into the solution and it measures the H plus concentration that's in that solution. Truthfully, it works off of voltages. So you actually calibrate it with like a pH of 7, a pH of 4, and a pH of 10, and then you stick it into your thing and it figures out the voltage and figures out the pH. Nice thing about the pH meter is it gives you the number right off the bat. You could also use pH paper, which if you ever tested like the pool and they buy those little pool strips and you do it and they got all the things, try to match up all the colors, kind of works the same way. You dip it in the solution, it has a little scale, you try to match it up. Not very super accurate, but it gives you an idea of the pH of the solution. We also will use litmus paper. And litmus paper really doesn't tell you the pH, but it will tell you if it's acidic or basic. So if you're using litmus paper and your litmus paper stays red or turns red, it's acidic. And if your litmus paper stays blue or turns blue, it's basic. Again, it won't give you the pH, but it'll tell you if the solution is acidic or basic. Usually if you use red litmus paper and it turns blue, that solution is basic. If you use blue litmus paper and it turns red, it is going to be acidic. In that case, I may have said it backwards there. If you use blue litmus paper to red, it's going to be acidic, and red to blue will be basic if you do that. So here is the pH scale, and again, some things that we see here. We have our strong base, which is really basic. We have our strong acid there that's really acidic, and we have something like pure water, which is a pH of 7. If you take water and you get the pH of it, will it be 7 all the time? It won't be. It will pick up some carbon dioxide from the air and create carbonic acid, lower the H plus concentration. Actually more acidic a lot of times. Sometimes people are surprised. It's like they measure some water, especially if it's been sitting out a long time. It'll be a little bit more acidic than they might think. That's why if you really want neutral water, sometimes when you're doing experiments, you'll oftentimes boil it and that'll get rid of the CO2, bring the pH back up closer to 7, and you could kind of use it that way. So we sort of touched upon this a second ago, and there is obviously similar scales to pH, and that's the POH. And so if we add in pretty much all of our sort of formulas here, we have our KW, which is our H plus times our OH minus, and that equals 1 times 10 to the minus 14. We have our pH, which is negative log of the H plus concentration. We have our POH, which is negative log of the OH minus concentration. Again, the relationship there, if you take the pH plus the POH, is going to equal 14. So again, that's sort of a quick way that you can do it. Now, a couple of other things to add to this is if you have the pH given to you, you could probably imagine directly from that, you could actually get the H plus concentration. So if you're actually given the pH, you could actually calculate the H plus concentration directly from that number. And that is the inverse log of the negative pH. Now, when most people hit inverse log on their calculator, that will pop up the 10 and the caret, also known as how maybe hopefully nobody's doing scientific notation anymore that way. That's why you don't want to do it. And we want to make sure it's negative pH. You could also, if you have the POH given to you, you could get the OH minus number directly from that, or the OH minus concentration is the same one, inverse log of the negative POH. POH. And again, that usually will pop up at 10 and a caret negative POH when you punch that in. How do you get to the inverse log on your calculator? Usually most people, top left button, there's a second button or a shift button, and usually your log button. So you hit that guy and then the log button, and that'll get you to the inverse log on it. Again, you want to use your negative button. Same thing with these formulas here, just like the other. If you have a display calculator, you're going to do inverse log negative in the pH. If you have a non-display, you actually have to start with the pH number, make it negative, and then do inverse log. So again, you got to go backwards if you have a non-display calculator with those formulas as well. If you have a display calculator, you have to go forward. So this gives you a wide variety of ways that you can actually get all that information, pH, POH, H plus, OH minus, just depends on your pathway. They all should give you the same. Again, I remind you that there is just one answer when you're asked, is it acidic, basic, or neutral? The reason people sometimes will give two answers is this. They will calculate the pH and go, cool, it's above 7, it's basic. Then they'll calculate the POH and go, cool, it's below 7, it's acidic. And they'll give the same two answers for the same solution. So I would always look at the pH value when you're trying to determine if it's acidic, basic, or neutral, because that is the scale most people have in their head. The pH scale is 0 to 7 to 14. Below 7 is acidic. Above 7 is basic. And obviously 7 is neutral. The POH actually runs opposite. So if you have less than 7 on the POH scale, it's actually basic. If you have above 7, it's acidic. And 7 is still neutral. So because most people have the pH scale in their head, I would always roll with the pH number to answer the question, is it acidic, basic, or neutral if you have the pH given to you. Don't give both answers, yes, because you don't want an X. Yeah, so just one answer to that question. Any questions on that there? Well, now we should see if our calculators work, perhaps. All right, there we go. All right, so for each of these solutions, let's just make sure we know how to do everything. So let's do pH, POH, OH minus, and is it acidic, basic, our neutral for the first one. For the second one, let's do H plus concentration, pH, POH, and is it acidic, basic? Take a look and see how you're doing on this. So again, because we have all those formulas, we have options as to how we want to approach it. And no way is right or wrong, really, depending on which way you choose. So since we're looking for everything on the first one here, I do have the H plus concentration, which means if I wanted to get the OH minus concentration, I could use the KW equation like we did before, and you can get the OH minus. I could also directly from the H plus get the pH. So that's what I'm going to do here because I have the H plus concentration. I'm going to go into the pH is equal to negative log of the H plus. And that's going to give me negative log of 3.6 times 10 to the minus 9. And that's going to get me here 3.6 to the minus 9. Looks like 8.44 as my pH. Again, here I still have the option to use KW if I wanted to, but to get to the POH, it is much simpler in a lot of cases just to use pH plus the POH is equal to 14 at this point. So I could do the POH would equal 14 minus the pH, which I just calculated. So 14 minus 8.44 is going to give me a POH, not that, 14 minus 8.44. It's going to give me a 5.56 here as my POH. Again, here at the end, I still have two options. Now that I have the POH, I could actually use that inverse log calculation, or I could still use KW to get to the OH minus. They both, again, should give you the same answer. So I'm going to do the OH minus is equal to the inverse log of the minus POH. So again, on your calculator, you're going to do inverse log, which should show up as on most people's a 10 and a caret negative 5.56. Again, to punch that in, if you have a display calculator, you would punch in the shift or second button, top left corner. You would hit the log button. You would hit your negative button and type in 5.56 and hit equals. If you have a non-display calculator, you would actually need to start with the number. So you would need to start with 5.56 and then hit your negative button to turn it into a negative number. Then you would need to go shift or second and log. So one of those ways should get you there. And in this case, I find it now on my calculator. There it is. I'll get you something like 2.8 times 10 to the minus 6 molar. Any questions on that calculation there? It's the inverse log of the negative pH, or POH in this case, negative POH. So that's the inverse log. Again, on most people's calculators, you got to hit that second or shift button, top left corner, and the log button on most people's calculators is how you get. It is on most, if you have a display calculator or something like that that displays it on most. When you hit this second and log, it'll usually pop the 10 and a caret usually up there. And that's how a lot of people did scientific notation before they did it correctly. Hopefully, that's a lot how people sometimes do it. But that is the way you want to do it. Again, if you wanted to still use KW, you could have done the OH minus is equal to KW divided by the H plus. That would give you 1 times 10 to the minus 14 divided by our 3.6 times 10 to the minus 9. And again, you would get the same answer, 2.8 times 10 to the minus 6 molar. So that again is your other option as to getting the OH minus. Any questions on any of those there? Acidic, basic, or neutral, this one? It is basic. We want to look at the pH here. It's above 7. It's going to be basic, yeah. Any questions on any of that there? All right, let's take a look at the next one, which is the OH minus concentration. I'll do it on here. So in this case, we were given the OH minus concentration, 9.2 times 10 to the minus 2 molar. Again, you have the same two options since we're looking for everything. You could use KW to get to the H plus, or you could go and calculate the POH in this case. And that's what I'm going to do. I'm going to calculate the POH first. Again, the name tells you what you need. POH means you need the OH minus concentration. Negative log of OH minus, going to give me negative log of 9.2 times 10 to the minus 2. Again, punch that in like we did previously, like you did the pH, exact same calculation as how you do the pH. Going to get you a 1.04 POH. Again, two significant figures, two decimal places. Yes, so that is what we're doing there. Again, at this point, the easiest way to get to pH is pH would be 14 minus the POH, and just take 14 away from it. The quickest way probably at this point to get yourself to the pH. Minus a 14, going to get you 1296 in terms of our pH. And now again, you have your option. You could still go KW to get to the H plus, or you could do the same calculation as we did previously using the pH. The H plus concentration will equal the inverse log of the negative pH. Once again, on your calculator, if you hit it, probably a 10 and a caret, make sure it's negative 12.96. And that's going to get you looks like 1.1 times 10 to the minus 13 molar. And this would be acidic, basic, or neutral, this one. This is going to be basic, again, looking at the pH. Any questions on any of those? Once again, you could have done 1 times 10 to the minus 14 divided by 9.2 times 10 to the minus 2, and you should get the same OH H plus concentration in this case. Any questions on that? Yeah, like it. This one we just did, so I'll just scroll it across there. All right, so why don't we just do what's asked here of this one? What is the POH here if we have 5.67 pH? All right, so again, this one is that relationship is pretty much the only way that you could probably want to get there. So once again, if you take the pH plus the POH, it does equal 14. And in this case, we have the pH given to us. So we're just going to subtract that to the other side, basically. And that would give us that the POH here is 14 minus the pH. So we'll go 14 minus 5.67. Going to get us a POH here of 8.33 in this case. Yeah. Any questions on that? Acidic, basic, or neutral, this one? Acidic, basic, or neutral, this one? It's acidic, yeah. So again, pH look at less than 7, so it is acidic, this solution, yeah. Again, don't give both, yeah, or all three. All right, let's do what it asks here. What is the H plus concentration if you have a pH of 3.14? All right, so again here, if you are given the pH, it again tells you in the name what you could get directly from it. pH means you could get directly from it the H plus concentration. And again, that is that one, that's the inverse log of the negative pH. You can make sure you do make a negative when you do it. So again, when you punch that into your calculator, depending on which way you need to punch it in, it will most likely pop up a 10 and a caret. Again, you're going to hit the negative, and we're going to go 3.14 in this case. And that is going to get us a 7.2 times 10 to the minus 4 molar. Once again, here we had two decimal places, gives us two significant figures going backwards. So that's what I was talking about earlier. It works both ways. Question on that there. Once again, if you have a display, that's going to be shift or second. That's going to be log. That's going to be negative and 3.14. Yeah. If you have non-display, again, it's going to be 3.14, your negative button. The shift or second button and the log button. So again, depending on which way you need to punch that in to get you there. Also, again, it may not give it to you in scientific notation, it may give you 0.0007, whatever it is there as well. Any questions on that there? Let's try one more here. What is the OH minus concentration if you have the POH? That's 5. Okay, so once again, if you're given the POH like we are here, it again tells you in the name that directly from that you could get the OH minus concentration. Good news is all these calculations are kind of the same depending on which one you're doing. It's really your pH, POH are similar calculations. H plus OH minus is as well. Inverse log of the negative POH here. Again, when you pop that in there, 10 carat negative 5.67. Gonna get you a 2.1 times 10 to the minus 6 molar. Again, it may give it to you in decimal form, 0.000021 as well. So either way is fine. Again, we got 2 decimal places, 2 sig figs when we go backwards. Any question on those calculations there? The key is just make sure you know how to punch it in correctly. Yes. All right, so up to this point, we kind of talked about pH and POH and calculating these things with sort of just a generic, you have H plus is this or OH minus is this. What happens if we're actually given a strong acid or a strong base? How do we calculate the pH? So for example, if we had HCl, it would break apart into, as we talked about, 100% H plus and Cl minus, which means if we had, for example, a concentration of 0.1 molar for the HCl, it is actually the H plus concentration that will help us calculate the pH, right? Is this negative log of H plus. That means we could do like we talked about with molarity. It is a 1-to-1 relationship between those two, which means the concentration of the H plus is 0.1 molar as well. And that's really all you would need to calculate here our pH. It would be negative log of 0.1. And that is going to get us here a pH of 1.00 in this case, right? So if you have the strong acid formula given to you and a concentration other than maybe sulfuric acid, it's probably going to be the H plus concentration. You could go right into it. What if you had a base, like say calcium hydroxide given to you? And let's just say this was 0.1 molar. When this breaks apart, you'll get a calcium ion and 2 hydroxide ions actually here. In the case of the base, we don't get H plus, but we do get OH minus, right? And from OH minus, we could calculate POH, right? So we could actually calculate the POH in this case if we get the OH minus concentration. It is a 1-to-2 relationship here, which means I need to take 2 times 0.1 molar, and that will give me 0.2 molar as my OH minus concentration. Putting that in here minus the log of 0.2 gives me a POH of we'll call it 70. I can get the pH from that by doing what? Taking, if I have the POH, all I have to do is take 14 minus that, right? So now I could just simply go pH is equal to 14 minus 0.7. And that is going to get me a 13.3 pH. That is definitely basic, right? And that is a base, so that makes sense, right? pH of 1 for my acid is a acidic pH, which we would expect. So sometimes you may not be given a generic form. You'll maybe given an actual formula of an acid or base. If it's an acid, all you have to do is figure out what the H plus concentration is and go into the pH, which in most cases will be the same as the concentration of the acid itself. If it's a base, you just got to figure out what the OH minus concentration is. and then go into the POH, subtract 14, you'll get the pH out of it. The good news is, since we don't really do weak acids or bases in here calculations, it's got to be strong acid or base if you're given a formula for it. Question on that there. So why don't you choose one of those strong acids? And what that really means is this perchloric acid, when it's in solution, will not stay together. It will 100% break apart into H plus and perchlorate here. And in terms of the pH, it is the H plus that's the most important thing. So since I know this is 0.025 molar, it's a 1-to-1 relationship between those two. 1 times 0.025 molar is 0.025. And that would equal my H plus. And that again is all I need to calculate the pH here. We'll pop that in there. And that's going to get us a 1.60, which is acidic pH. And that makes sense since that's an acid. So I would say probably in most cases, if you have a formula for a strong acid, that's going to be probably the H plus concentration. And you can probably go right into your pH equation. Question on that there. Question on pH, POH, H plus, OH minus, how to calculate any of those things. All right, the last thing we're going to kind of talk about here with acid and bases are buffers and sort of what buffers are and sort of how they work and what they're made up of. So let's take a look at sort of a buffer and sort of what it is. So a buffer is a solution that can resist changes in pH even when you add more acid or base to it. So the first misconception people have about a buffer is it's a neutral solution. That is not correct in all cases. You could have a buffer that's neutral. You could also have a buffer that's acidic. You could also have a buffer that's basic. You can make a buffer at any pH you choose. So you can actually choose a pH and make a buffer solution. What it means is if you have a buffer, let's just say the buffer was at a pH of 5 when you started. You made this buffer at a pH of 5. When you add acid to that buffer, it pretty much will stay near a pH of 5. Will it go down a little? It will go down just a little bit, but it will not go from like a pH of 5 all the way down to like a pH of 1. So it won't have a big jump in pH. It's basically able to stay near that 5 pH that you made it. Now, if you have that buffer that you made at a pH of 5 and you added base to it, it also would basically be able to stay around 5. It may go up a little bit, maybe 5.1, 5.05, but it will not go from like a pH of 5 all the way like a pH of 14 if you add some base to it. So again, the first misconception is people always think a buffer has to be neutral, and it doesn't. It could be any pH you want. It just means whatever pH it starts at, if you add acid or base to it, it pretty much will be able to stay right around that starting pH. It will not vary very much in terms of pH. A buffer is made out of one of two combinations, either a weak acid and what is referred to as the salt of its conjugate base, or you can make a buffer out of a weak base and the salt of its conjugate acid. The relationship between a weak acid and its conjugate base, or a weak base and its conjugate acid, is still the Bronsted-Lowry definition of 1H plus difference, basically. Okay. So for example, you could have a most popular buffer example ever used, which is acetic acid and sodium acetate. That is a weak acid, and I know it's weak because it's not one of the 6 strong acids, so I know it's weak. And this is his conjugate base. It's really the acetate part here that is the important part to the buffer, and the acetic acid. The only difference between those two is 1H plus. Why it's called the salt of its conjugate base is it's got a sodium there just to hang out and balance out the charge. The sodium is not doing anything. That's basically makes it an ionic compound. You could also have a buffer like HF, which is a weak acid, and NaF, which is conjugate base, or the salt of its conjugate base. Again, here it is the HF and the F minus. That's actually the active part of the buffer. This is the acetate over here. That's the active part of that buffer on that side. You could have something like NH3, which is ammonia, and NH4Cl. That is a weak base and it's conjugate acid. Here it is actually the NH4 plus. That is the buffer part. The Cl is just a spectator ion. It's hanging out, balancing out the charge. And maybe a little sodium bicarb, right? And sodium carbonate buffer, like maybe in the blood. Yeah, so you got a little bit of that things happening. All these guys are related to each other basically by 1 H plus difference. The one thing that you cannot have to make your buffer out of, a buffer can never be made out of a strong acid or a strong base. So you can never have a buffer that's made out of a strong acid or a strong base. If you see a strong acid or a strong base in something and they ask you, could that be a buffer? The answer is no. And the reason is no is because it will completely break apart and you will not have the parts that you need for the buffer to work properly. A weak acid or a weak base is a weak electrolyte, which means it's actually able to keep both parts that you need of the buffer actually in the solution at the same time because it sets up that equilibrium. So what makes a buffer able to work is, go back this way, there we go. What makes a buffer able to work, for example, let's take the HF NaF buffer. This again is our acid. This is our base part of the buffer. So when you would make this buffer, you would put that hydrofluoric acid, which is a weak acid. It will set up that equilibrium. You will make H plus and F minus in there, which means in your buffer solution to begin with, you have an acid part to it. And you have a base part of your buffer. And that is critical for how a buffer is able to actually work, is both of those things has to be in there to begin with when you make your buffer. So how does it work? Well, let's take a look at what would happen if I added HCl, strong acid, to water. Water is not a buffer. So if I do that, when I add HCl, which is a strong acid, to water, it's going to completely break apart into H plus and Cl minus, right? So if you look at that water solution, you just put in there a bunch of H pluses and a bunch of Cl minuses, right? The amount of H plus just drastically went up, yeah? So you just increased a lot of H plus, and when the H plus concentration goes up, the pH goes way down. You just put a bunch of H plus in there. You're going to see a huge drop in the pH of that. Maybe you have your water at 7, you add that acid, it's going to drop all the way down to maybe 2 or 1, a really big jump in pH because you just influxed into there a ton of H plus. Now, if you were to put in there into water some sodium hydroxide to water, it will also break apart into NaOH because it's a strong base into Na plus and OH minus. And what will happen in that solution is you will have a bunch of Na pluses, but you'll have a bunch of OH minuses, right? So now you just put a ton of OH minus into water. and that's going to cause the OH minus concentration to go up. The H plus concentration will go down, and the pH will go way up. Yeah, so you'll see that jump for like a pH of 7 to like a pH of 12 or something like that, depending on how much you have. So when you add acid or base to a non-buffer like water, what you're doing is you're introducing a lot of H plus really quickly when you add the acid, cause a really big jump in pH because there's a lot more H plus than should be in there. And when you add base to water, which is not a buffer, you add a lot of OH minus really quickly, and you see the pH go really up. Now, if you added that same HCl to my buffer over here, if I added HCl, which is an acid, it will go and actually react with the base part of the buffer. So when you do that and you put it in here, that's H plus and Cl minus. And when that comes in, that H plus will actually go and react with the base part of the buffer, and it will actually make this. You'll add HCl plus the sodium fluoride. It will make some sodium chloride and HF. It will actually make the other part of the buffer. But more importantly, what you do not see in this equation that you do see when you added acid to water is no more free H plus. So because that H plus that comes in from the acid gets tied up, it's no longer able to float around freely. So all you have in that solution is the amount of H plus you started with, basically, maybe a little bit more. And that's what's able to keep the H plus concentration stays relatively constant because this incoming H plus gets tied up. And because of that, the pH will stay relatively constant as well. And I say relatively constant because if you're watching it, you will see the pH go down a little bit. The same thing happens when you add base to it. If you add base to a buffer, instead of that OH minus being freely floating in there, the OH minus, the sodium hydroxide, for example, would react with the acid part of the buffer in that case. And you would make salt and water. So you'll make water, which won't affect the pH. And really that OH minus gets tied up in water in that reaction. And what it does is it prevents the free formation of OH minus in that solution. Again, because the OH minus stays relatively constant, the H plus will stay constant and the pH will stay constant. So a buffer works because it has an acid and base component. So when you add additional acid or additional base to your buffer, it prevents the formation of free H plus when you add acid or free OH minus when you add base. And both of those things, because they're not added, keeps the H plus concentration relatively constant, and that in turn keeps the pH relatively constant in that case. We'll talk a little bit more about it next time, but that's the general idea there of a buffer.